are never satisfied with knowing, you know, when you're a little kid, someone says, oh yeah, there's a lot of something. Well, they don't, kids want to know, well, how much, how many, and so forth. Same with adults. We are never satisfied with enough, okay? Or there's plenty, or there's tons, or whatever. So we want some finite numbers here. So this first, this whole section is on counting principles. There are three counting principles that we're going to be talking about. One of them is the fundamental counting principle. This is just an overview. You don't have to bother to take notes on this slide. The second one is called permutations, right? And this third one is called combinations. And we want to make sure that we know the difference between permutations and combinations and when to use the fundamental counting principle. Okay. Fundamental counting principle. Okay. So that's kind of an overview of where we're going with this. So they're used to find the number of possible outcomes for a sequence of events. The first one, the fundamental counting principle, is used to find, you know, of course, how many times that something can occur. And you always want to ask yourself with these kinds of problems whether it is with or without replacement. Okay, and I'll explain what that means in just a moment. So we have a combination lock. All of you have a combination lock on your locker. I didn't check to see if the numbers were the same if you have 0 through 39 like this particular lock does. But you have a certain number of possibilities, right, that you can go to. Is it 50 on yours? Okay, I should have taken a picture of your locks. 50? Oh, no, I didn't. Okay, well this particular one only has 0 to 39. Okay? And it's like yours. You have to go to the first number, right? And then you pass the second number, go to the second number, and then pass it twice and go to the third number. So we have 3 numbers that we can use or that are required to open the lock. So when I see a problem like this that's a fundamental counting principle type of problem, I ask myself, first of all, can I reuse those numbers? Yeah, I could have 1, 1, 1 as my combo. I'd be very lucky if I did, right? Because it would be easy to remember. So because we can reuse those numbers, that's considered with replacement. Okay, we can reuse them over and over and over again. Okay, so how many possible numbers could be our first number? 39. Actually, is it 39? Because we could also have 0, right? So it's 40 for our first choice. Okay, and then because it's with replacement, we could use any of the 40 for our second number, right? And we could use any of the 40 for the third. So when we want to know how many possibilities there are, we simply multiply the 40 by the 40 by the 40. So 4 times 4 times 4 is 64, right? And 10 times 10 times 10, 1,000. So we've got 64,000 possible combinations without having anyone have any 2 locks using the same combination. So you have a 1 in 64,000 chance of opening someone's locker if they're using this type of lock if you don't know anything about their numbers. Make sense? Okay, so next example. License plates. Okay, about 6, 7, 8 years ago, Nebraska was running out of numbers on their license plates for people in Sarpy County, Douglas County, and Lancaster County, the 3 biggest counties. And it was worse for Sarpy County because our county number used to be 59. And Douglas County was county number 1, and Lancaster was county number 2. Lincoln, anybody in Lincoln got 2 plates, or number 2 plates. Anyone in Douglas or Omaha area got a number 1 plate, right? And anyone in our county got a 59. Okay, they changed that so that the 59 would be a vertical 59, but it still didn't do the trick. Okay, because we were running out of plates for all the licensed vehicles on the road. So for these 3 counties only, Nebraska has gone to an ABC 1, 2, 3 type of plate, unless you buy a specialized plate. Okay, so how many possible combinations of plates do they have for these 3 counties then? In the first spot, we have how many options? 26. In the second spot, can we use any of those same 26 letters again? You bet. So 26 again with replacement, right? And third spot? And then how many possible options in the first one? Okay. 10, 0 through 9, right? So there are 10 possibilities here. Because I could put a 0 or a 1 or a 2 or a 3 on up to 9. Yep. Okay. So we have 10 possibilities there, right? How many in the second numerical spot? Because we can replace, right? Okay. They did actually put in like a specialized Husker plate so that it can have all 7 letters. But that's the specialized plates, not the generic that have. Okay. Okay. Make sense? So for the generic plates, we have this many possibilities. So then you would take 26 times 26 times 26 times 1,000, right? And we get how many possibilities? 17,576,000? Okay. So that's how many license plates that we can have in Douglas, Sarpy, or Lancaster County. Okay. Now, if you ever leave this part of the state or you notice someone from out of the counties, you'll see that they'll have a county number or a plate that looks a little bit different. It'll be like 12 county, 12 and then something. 12 county was Knox County where I was from. 13 county was Cedar County. If I see 7 county, I know it's Dixon, and so forth. So if you're from a rural area, you'll recognize the county number and know roughly where someone's from. Okay? Questions on this one? Okay, so next one. Here's another one. We're talking about lineups now. We have 9 players, 9 baseball players, and we want to decide what the batting lineup's going to be. And we want to know how many different possible ways we can rearrange that, provided that the pitcher can't bat in the first 4 spots. Okay? Typically, your pitcher's not one of your best batters, right? So you want to load your best batters in the front. So the coach says, hey, no pitcher in the first 4 spots. So how many blanks do I need? 3, 4, 5, 6, 7, 8, 9. Okay. How many different players could bat first? 8, because the pitcher can't start first, right? Then 7, because that same person it's no replacement this time, right? Because the person who bats first can't bat second, right? So pitcher can't go first, and then the pitcher and whoever batted first can't go second, right? After the 4th. Okay. Then 5 again. And we're going to multiply them together. So this looks a lot like 8 factorial, right? But it has an extra 5. So if you want a shortcut, take 8 factorial times that 5, and you'll get your answer. Okay? So the coach could choose 201,600 possible different lineups. Okay? Now, on your graphing calculators, I found another special trick. Okay? At least on mine, I know it works, and I know it works on many of your others. If you have a TI-84 plus CE, for sure, I know it works. When you're on your calculator, if you go to alpha, which is your green button, and then try F2, the function, the alpha of window. So first of all, type in 8 to get an 8 factorial, right? So type in 8, and then alpha F2, alpha window. Some of the newer calculators will give you a little shortcut menu that has a factorial button on it. Number 9 is factorial. 8 is NCR, 7 is NPR. Okay, so it was alpha and F2. And then you're going to try, I'm not sure if that one's going to work. Try going down, seeing if you can arrow down. Nope, those are the only options you have. So that one must not have, was it alpha F2? Okay, so that one must not have it. Okay. But I know the CEs do. Okay, so that gives you a shortcut method, an easier way to get to factorial. Okay. And I can help you find it a little bit later. Okay. All right. So questions on this one? Okay, let's keep moving. Olive Garden, last year about the time I was teaching this to Algebra 2 students, was having a tour of Italy. And their tour of Italy gave us lots of different possibilities for meals that you could have. So let's say that you decided to be an Olive Garden addict and go to Olive Garden until you had every one of these possible tours of Italy. Let's see how many times that you would have to go. So you start out with unlimited soup or salad. So those are your two choices there with breadsticks. So in your first part, you have two options, right? Okay. Then they said, guess what? Now you get to choose a specialty item. And your specialty items are either a shrimp ravioli with lobster Alfredo, chicken parmigiana, lasagna classico, or a new Tuscan sirloin T-bone steak. So we have 4 possibilities. And then they said, guess what? Now you choose a premium filled pasta. Do you want tortellini al forno, chicken marsala ravioli, or cheese ravioli with marinara? It's 3 possibilities. And then they said, guess what? Now you get to choose a signature pasta. And with that signature pasta, your choices are spaghetti with meat sauce, fettuccine alfredo, or ziti with 5 cheese marinara. So 3. So if we multiply those together, 72. 72 different times that you could go there and get a different meal each time. Okay, so 72 different possibilities. All right, questions on this one? That's the fundamental counting principle. Okay, just put blanks out there and decide how many possibilities I have with each of these blanks. Okay, all right, so next one. Now we're talking about our second counting principle, and the second one is called permutations. And when you think of permutations, remember that order matters. Okay? Order is very, very important. How do you arrange people? How do you choose a winner? How do you choose the president or a leadership team, right? So order matters with permutations. So number of permutations of n elements. In other words, how many permutations are possible if we wanted to list the numbers 1 through 6 and the order was important? We use the formula for permutations as n factorial. And that's only if you're using all of your choices. Okay? This is like saying n factorial over n minus r factorial, which is all of them, so over 1 factorial. In other words, if the order matters and I want to list 1 through 6, not using any of them twice, I would have 6 factorial possible options. Okay? And 6 factorial is 1,440. Okay? That's how many ways I can list the numbers 1 through 6 without having any repetitions. Okay? The next piece of that is how many permutations of n elements can be taken r at a time. So now I'm not using all 6 elements, I only want to use a portion of them. Okay? In other words, here's 12 runners and they're running in a race. Okay? Cross country, track, whatever. We want to know how many ways these athletes could come in first, second, or third place. Okay? The formula for permutations is similar to what we were using yesterday for combinations, but what's missing down here? The r factorial, yep. We have n factorial over n minus r factorial, and we're missing that extra r factorial. Okay? So when we are working this guy out, we want to plug in our smartboard again. Come on, there we go. All right, so then when we're working this one out, we're going to take 12 runners and got to get it to remember that I'm now plugged in. Oh, not supposed to go there. It's supposed to go here. There we go. All right, so we want to take 12 runners and we want to arrange them by 12 minus 3 is 6 factorial. Because it's 12 runners taken 3 at a time, placed 3 at a time, first, second, and third. And so that means that you take 12 factorial over 12 minus 3 factorial. Sorry, should be 9. I'm thinking about my smartboard and how I managed to accidentally erase or unplug that. Yes, sir. Because when I took 6 factorial, it's 6 times 5. Could be. Maybe I made a mistake. Could be. 6 times 5 is 30, times 4 is 120. Yes, 720. My fault. Thank you for keeping me honest. You're right. Don't want to confuse anybody. All right, so what was 12 factorial divided by 9 factorial? 1320. Okay. Because we're taking 12 times 11 times 10, right? Over 9 factorial, those go away. And 12 times 11 times 10, 110 times 12 is 1320. Okay? Right, because the 9 factorials will cancel. Yep. Okay? Sometimes it's faster to do those than it is to plug it in the calculator. All right, questions on this one? Okay, next one. All right, so now we want to know how many ways can we arrange 7 people in a line for a photo. Okay? How many ways can we arrange 7 people in a row to take a photo? Okay, no replacement, right? Because people can't be in 2 places at one time. So 7 factorial. Because that's no different than 7 people being arranged one at a time, right? So 7p1 is the same thing as 7 factorial. Because that will get you 7 factorial divided by 7 minus 1, 6 factorial. Oh no, 7, arrange 7 at a time. My fault. 7 people arranged 7 at a time. We want all 7 of them to be lined up. So 7 divided by 1 factorial. And what do we get? 5040. Lots of possibilities, right? Okay. Questions on this one? It's a lot, isn't it? Okay. All right, so next one. That's why we usually say highest to lowest or something like that. Put the short people in the middle and the tallest on the outside. All right, so now we want to talk about distinguishable permutations. Again, order matters here, right? But we want to be able to distinguish between them. So when we're arranging letters, for example, the letters sometimes repeat. And we want to know and be able to distinguish between those particular patterns. So when you want a distinguishable permutation, you take n factorial and you divide it by how many times each kind of object occurs. For example, the word banana. Okay? The word banana has some repeat letters, right? So we want to know that we have a unique word, banana. So for example, banana with this letter, this fourth letter in place of the first or the second is the same as banana. Can't tell the difference between them, right? They're not distinguishable. Okay, so we want to take out those same repetitious ones. And to do that, we say, how many letters in banana are there? 6 total, right? So 6 factorial. Okay, now how many B's are there? Just 1. So that's a 1 factorial. How many A's? 3. So we're dividing that by 3 factorial. How many N's? 2. So 2 factorial. And if you don't want to write the 1 factorial over and over again, you don't have to when there's a unique letter. Okay? So we would take 6 times 5 times 4 times 3 times 2 times 1, divide it by 3 times 2 times 1 times 2 times 1. And how many possibilities are there? Everybody wants to say it out loud. 60, right? Okay. So 60 possible combinations. So you would need to put this in parentheses if you're dividing it. So on your calculator it's 6 factorial, and then you're dividing that by, in parentheses, 3 factorial times 2 factorial. Because otherwise what's going to do is it's going to take it divided by 3 factorial and then take that answer times 2. And we don't want to do that. We want to divide it by the 2 as well. So 3 times, yeah, or actually it's 3 times 2, yep. Yep. Make sense? All right, last example on this piece of the distinguishable. How many ways can we rearrange the letters in Papillion, for example? 9 factorial on top, there are 9 letters. 2 P's, so 2 factorial. 1 A, so we can leave that 1 factorial out. 2 I's and 2 L's. So we would take 9 factorial divided by 8. Right? Mm-hmm. You don't have to. If you want to, you can, but 1 factorial is not going to do anything to our net result. So we decided to not bother with the A's here and the N. We didn't write the 1 factorial for each. Okay, other questions? All right, makes sense? Let's keep moving. Okay, so combination rule. We use the combination rule when order does not matter. Okay, they don't have a special title. They're not the president, vice president, and secretary. They're just members of a committee. They don't have a placement. We're not worried about whether you are picked first, second, or third. You're just part of a team. Okay, so when the order doesn't matter, we use a combination. So we are forming a 12-member swim team, 6 girls and 6 guys, from 10 girls and 15 boys total. How many different teams are possible? Well, to do that, we're going to use the combination rule. So we're going to say that we're going to take NCR, which is the n factorial, over n minus r factorial times r factorial, like we were doing yesterday with our binomial theorem. Okay? So we're going to pick girls team first, maybe. How many possible swim team members are there? 10. 10 girls to choose from, right? And how many are we choosing? 6. Okay, how about boys? We have 15 boys and we're choosing 6. Okay, doesn't matter if you were listed first on the list or 6th on the list, you still made the team, right? So the order doesn't matter here. So, exactly. So 10C6 gets us what? 210. And then 15C6 is, and what are we doing with these two numbers? Multiplying them together. And so we get a big, huge number of lots of combinations for our swim team. God bless you. Okay. Questions on this one? All right. So, in summary, when you're trying to decide whether it's a permutation or a combination, you have to decide if order matters. Do we have a special, are we putting them in a row? Are we giving them a special title? Are we giving them a placement, right? Then order matters, and that's a permutation. So you're looking for words like order, arrange, award, seating, rank. But if it doesn't matter, if we're just selecting or choosing or picking, right, not placing, then you're talking about a combination. And with the fundamental counting principle, you just have to decide if you can replace those things or not. Can we use that number over again? Can we use that letter over again? The order on permutations does. Combination does not. Okay. The distinguishable, it also matters, exactly. It's just that we have repetition, so we want to be able to tell whether these two are the same or not. We want to get rid of the same thing over. Okay? All right, assignment